All right, so hello everyone. Today is June 15th. We are going to continue on with our Chapter 7 homework. We left off on question 26, so we'll begin on question 27. So we'll finish up the chapter homework pretty quick, so we'll just move right into the Chapter 8 PowerPoint notes. I have those posted on Blackboard. I don't think we're going to have time to go into the Chapter 8 homework today. As we get onto these, and as we get deeper into the textbook, the amount of material and the amount of stuff that we cover just becomes more and more, which is okay. And I want to take my time with it. So another big announcement that I have is that the exam is due tonight at 11:59 p.m. I know many of you have not taken the exam. So if you are in that category who has not taken the exam, I'll look up the exact numbers right now. Let's see. So I have 14 out of 32 students who have completed the exam. So, that means, over half the students have not completed the exam. So if you're in that category, there's going to be no extensions tomorrow for the exam. So, if you're here right now and you're listening to this, please, complete the exam. You're given more than enough time. So if you are here tomorrow and, for some reason, your exam is not completed, that's going to be a 0. So I don't want to do that, but, you were given all day Saturday, Sunday, Monday, Tuesday, and today. So I think that's enough time to take the exam. So, please just, for your own sake, just get it done. So let's go on to question 27. All right, so I got my pen going. All right, so 27, let me pull that open. Okay, it says 27 says, consider the pair of reactions. They give you 1, 2, 3. They give you a not a methyl chloride, but a propyl chloride, and the reactant with bromide or bromine and iodine in 2 separate reactions. This is going to be an SN2 reaction. So you have some type of alkyl halide 1, 2, 3 with this X. That X is chloride in this case. And it's going to react with some other halide in an SN2 fashion. So that's what's going on. So product 1 and product 2, they're very similar. We'll have that propyl group. And the only thing what we're going to place it is with the appropriate halide. And that's a SN2 reaction. And recall that SN2 is concerted. So it says identify the mechanism. So both are SN2. And then it says it wants you to compare the rates between reaction 1 and reaction 2. Reaction 2 is going to be faster than reaction 1. So you're going to select reaction 2. And the reason is because iodine is a more effective nucleophile on water. So that was that reasoning. All right. So let's go on to, I guess it'd be question 28. So it says for 28, consider the reaction of an alkyl bromide with hydroxide. Let me switch the slide. I have an alkyl bromide. We're going to react it with some type of hydroxide. You know, what are the possible reactions that we can have? Well, we can have an SN2 and we can have an E2. So if we have an SN2, let's focus on that. That's all this is going to be right here. So that's going to be your SN2. Now, if we have an E2, we have a hydrogen here. That oxygen is going to take that proton. It's going to form a double bond, and that bromine is going to be a good leaving group. So there are options. So we will have two different products. So we have this product. We also have the E2 product. Here's your E2. Here's your SN2. Sorry about that. My computer takes phone calls. That's just what the system does. So anyways, the SN2 and the E2 reactions are right there. I think that's all they want. Yeah, that's it. So I don't see any questions, so I'll go to the next one. Let's see. So question 29, it says complete the curved arrow. So we have this thing right here. And if I don't put anything on here, it's implied that there's a carbon right there. We can put a CH3. Deuterium. On this other side, we have hydrogens instead of deuterium. And I think that's a chloride. Yeah, that's a chloride. So we have to just draw the curved arrow. So we have this OH group. It's going to come in. Chloride's a good leaving group. So we have that. So then we're going to form the product with the that says select the option. It is an SN2. So why don't you, I'm gonna pause this so you can put in the correct answer. All right, so where did that go? Okay, yeah. So we're gonna move on to question 30. So with 30, we have it just wants the curved arrows right here. So we have this thing right here. We have a strong acid. So we know that we're going to transfer a proton right there. And what we're going to have left is our iodine. And then we'll have this group right here, which now we have water right here. So we know that water is a good leaving group. So it'll take off. Then once that takes off, then we have our carbocation. We still have this iodide out there. We'll draw it closer. That can come in and attack right there. And then our final products would be H2O and the iodide product. So that should work for you right there. And that's it. So we only had 30 questions. What I'm going to do is I'm going to go ahead and save this. So I'm going to pause the recording and then I'm going to upload it. So I'll give you a brief. So take a moment to open up the Chapter 8 PowerPoint slides. Does anyone have any questions on this homework? All right, so I don't see any, so I'm going to pause the video momentarily and I'll be back. I'm just going to load this up and then we'll continue on. All right, we're back. If you're listening asynchronously, it'll be like we never left. But you should have your Chapter 8 PowerPoint notes open right now. There's a lot going on in Chapter 8, but I found a really good section in Chapter 8. If you flip to the back, I'm not going to do this, but on your own time, flip to the back of the chapter. It gives you some mechanisms that's really important in Chapter 8. And I can go ahead and show you, in the end of this PowerPoint slide. No, let me open this up. So if I just flip through to the end of the slides, it gives you some really good mechanisms to go over. So I think that the end of the chapter actually does a better job because it shows you the arrow pushing. So if you can take a look at that, on your own, I think that would really help you as far as with the arrow pushing. The end of these slides, you can use, what you learn in this chapter and on the back of the chapter for the Chapter 8 and apply that knowledge, to solve questions like this. For instance, I know we haven't gone over this yet, but we will. I'll just give you an example real quick. We're going to be going over, there's my pen, how this is going to happen right here. And then, this bromine is going to add. So, these are going to be topics that we talk about today and maybe next lecture. But I think the back of the chapter does really good as far as showing you the different arrow pushing. So I just wanted to point that out. So let me go to the top of the PowerPoint notes now. Discard that. So we're going to talk about a bunch of different reactions. Some of these we're going to be, more selective. Some of them they're going to be not very selective, and you'll see what I mean as the chapter goes on or as the slides go on. So an introduction to addition reactions. So we're going to be adding something. It says addition of X and Y. So that's what this chapter is about. And you kind of saw that briefly, when we had that bromine complex. We're going to be adding here. We're going to be adding here. This is going to be a release, and then that bromine is either going to add to this side or to this side. So that's what's really going on. So the pi bond is electron pair donor, and it can act as a nucleophile, and they're showing that to you in this slide. and the book does talk about naturally occurring acyclic alkenes, you know, hydrocarbons with double bonds. So they just wanted to give you some examples. And they give quite a few examples. Something that's you know, that you should take note of is that alkenes are critical precursors in the chemical industry for ethylene and polypropylene. These two products, I guess, you know, they're made from petroleum, but these two products are precursors to other, you know, products that we use, such as plastics and all different types of materials out there. So, you know, I just wanted you to be aware of that. Propylene can make polypropylene. You know, I'm going to be buying carpets soon, so they're going to use propylene. That propylene is used to make polypropylene. And you know, they get this, some of this they can get this from like reused plastic bottles, but some of it they have to get through petroleum. And as you know, that the price of barrel for petroleum has gone up, so the price of materials are going to go up. Here's that propylene, and they can make polypropylene out of this. So there's a bunch of different stuff that they can make out of these. And you know, companies like Procter and Gamble and 3M, they buy ethylene and propylene from chemical companies such as, like, I don't know, when I was in Lake Charles, there was a company called Sasol down there, and they took petroleum and they made ethylene, and then they sold that ethylene to chemical companies. They go over some naming. This should be some review. Alkenes are given IUPAC names using the same procedure to name alkanes. So this is just a review. You know, pentane versus pentene. One has, you know, pentane has no double bonds. Pentene has, you know, that double bond right here. We have octane and we have heptene. So this would be 1, 2, 3, 4, 5, 6, 7. So that's how you get the hept right there. You want to identify and name the substituents. Now, why is this the correct name right here? Because we put the lowest number here. Here, you know, we're starting at a 5. So the locant of the double bond is a single number, and as a number indicating where the double bond starts, the alkane above is located at the 2 carbon. And it says give the carbon-carbon double bond the lowest number. If we start the other way, we're not giving it the lowest number. You know, 2 is less than 5, so we're gonna, this will be correct as far as how the IUPAC wants the naming done. Just some more naming. You know, this is a 5,5. At the 5 position, there's a methyl group. At the same 5 position, there's a methyl group, and at the 6 position, there's a methyl group. That's how you get trimethyl. So 5, 5, 5, 6 trimethyl, 2 heptene, and they're both written correctly. It says, note that this alkene is in the E configuration, right? So, you know, that's something to think about. And that's because you can see it's going opposite sides. Now, if it was going to go to the same side, which it's not doing, but this would be the Z configuration. But that's not, and we'd have to get rid of this. But that's not the case for this compound. It's in the E configuration. All right, so addition and elimination are equilibrating reactions. Which side is favored depends on the temperature. So the higher the temperature, the more important entropy becomes. You can see that in this term right here, we have delta G equals delta H plus T delta S. If you really increase that temperature, this term is going to become more significant. If you decrease the temperature, this term becomes less significant. So, if we had a continuum and we said, okay, we're going to have high significance, and here we're going to have low significance. If we increase the temperature, the higher we go on the temperature scale, we're going to go to a higher significance. If we decrease it, we're going to go to a lower significance. But see that the term is not significant. It's whether it's going to be higher significance or lower significance. So hopefully that makes sense. Because you might think that, well, it's just not going to be not significant, but it's just going to have a lower significance. It's a play on words, but hopefully that makes sense though. Addition reactions are favored by enthalpy. So we had so sigma bonds are stronger, more stable than pi bonds in this case, where we have this adds up to 166 kcal per mole. This sigma bond, these two sigma bonds, they add up to 185. So if we take the bonds broken minus the bonds formed, we get minus 19. So thermodynamically, this will be the more favored product on this side right here. It says addition reactions are not favored by entropy. Two molecules combine to form one product. Entropy decreases. You can see that, here we have one, here we have two. Now we're forming just one product over here. So entropically, this doesn't want to form, right? It'd rather be in this side over here. So then it really kind of depends on the temperature, right? And this next slide really talks about this. Remember, delta G equals delta H. Oh. So when the temperature is more significant at a higher temperature, we're going to get the two products. When we have a lower temperature where we, lessen the significance of temperature, we're only get one product. All right. So hydrohalogenation, addition of HX so that X is, some type of halide to an alkene, can use HCl, HBr, or HI. If an alkene is not symmetrical, then two regioisomers are possible depending on which carbon gets the hydrogen. And they talk about, more about that regioselectivity on the next slide, where they say hydrohalogenation is regioselective for the Markovnikov addition. In 1869, Markovnikov observed that the hydrogen atoms tend to add to the carbon already bearing more hydrogens. So that means in this case right here, if we just, we draw this right here, which one has more hydrogens? Well, this one has more hydrogen because it has one versus none. So we're going to put the hydrogen at this position right here then. And this is the Markovnikov addition, where you put the hydrogen tends to add to the carbon already bearing more hydrogens. And the reason being is, let's just say this, added there, and now we have a tertiary carbocation versus it'd be a primary carbocation. But you can make it so that you can get the anti-Markovnikov addition, and they show it to you on the next slide. It says when peroxides are used with HBr, the opposite regioselectivity is used. So, if you don't want to put the, the bromine, right here, then you can know if you put these reaction conditions, you can get the bromine on the other side. It says the reaction mechanism must be different when peroxides are present. If we just take a look on this slide, we added the bromine to the more substituted side. And here we added to the less substituted side. And that's because we changed the conditions, I mean, we added that peroxide, so we're changing the reaction conditions. And they do a good job here showing to you, we're gonna get the Markovnikov addition here, or we're gonna put the Br here. And for the anti, we're gonna put it right here. And then they tell you, and they don't tell you, they just ask you, draw the expected one. So you would have it here. And then for this one, you'd have it here. Because remember, you're using a peroxide on this one, you're using just HBr. And you can check your answer on the next slide. So, the top one is the Markovnikov. The bottom one is the anti-Markovnikov addition. Oh. So the mechanism of a two-step process. It does show that it's in equilibrium on both steps, so it can go back. But if we go into the right, here we're adding a proton to the side that has more protons because there's a proton right here that they're not showing. So now we would actually have two protons. If we call this one A and this one B, this would be B right here. This would be A. We have a tertiary carbocation. This bromine adds by nucleophilic attack, and we have our compound. All right. So hydrohalogenation, the step with the highest activation energy is the rate determining step, which is the formation of the carbocation intermediate. So our rate determining step is we got to form this carbocation intermediate first. This is our activation energy barrier. Oh, it wanted to erase it on me, didn't it? So the anti-Markovnikov pathway, remember, we're going to, now that hydrogen is going to be added to the place where we have the, well, here we'd have one hydrogen here still. So we're going to add it to the one that doesn't have any hydrogens, and we put it on the right-hand side. So we have a secondary carbocation, and then this can add right here. And they show you the Markovnikov pathway. So they do a good job of showing you the tertiary carbocation versus the secondary carbocation. The Markovnikov product is formed through a lower energy transition. And why is that? Why is the Markovnikov, a lower energy transition than this one? Well, remember, if you think back, I don't know if it was 5 or 6, we talked about the tertiary carbocation being lower in stability, not lower or higher in stability, because that charge is more stable. Remember, these carbons are electron donating, so they're going to be able to donate some electron density there. So we're getting it from 3 sides. Here, we're only getting it from 2 sides. So that's why you see this difference in stability, that the tertiary carbocation is lower in energy, which makes it more stable. So hopefully that makes more sense why we're putting it right there. It says hydrohalogenation may result in the formation of a chiral center. There are actually 2 Markovnikov products formed in this reaction. And that's because it can attack from either the up position or the down. So it could attack here or it could attack here. Now remember, if we added the hydrogen here, right? We're not going to have that double bond here, and that nucleophiles can attack either from the up position or from the bottom position. And that's how you get the RS. And they do a pretty good job on the next slide. I just want to turn there, and it's the same concept. And they're showing you how it can attack from the upside or from the bottom side. So you could either get the R or the S. I recall, though, from just, chapter 7, that carbocations can rearrange. I guess we learned this in chapter 6 too. We can have a hydride or a methyl shift, or, a hydride or a methyl shift. So we can have a hydrogen shift, or we can have a methyl shift. If they can become more stable, that's the key word, if they can become more stable. So in this case, we have a secondary versus a tertiary when we get that hydride shift. So recall that a tertiary is more stable than the secondary. So, more than likely we'll get this shift unless we change the reaction conditions where this can happen. And we can do that, but if just in this general case, this is not going to happen under these set conditions. But we'll learn in this chapter, how we can make that from not happening. So when carbocations rearrange, or so when carbocation rearrangements can occur, they do occur. And you can see that we get both products, right? But one is slightly favored over the other one because we form a tertiary carbocation versus a secondary carbocation. So this would be your tertiary, your secondary. So we're getting a little bit more of the tertiary products. It says the components of water, H and OH, are added across the pi bond. Acid catalyzation follows the Markovnikov regioselectivity. So that means, if we had this, this right here, this would be positive. We're going to be adding this right here. It's following the Markovnikov regional selectivity. It says sulfuric acid is commonly used as an acid catalyst. And what that means is now it can donate the protons and we form H3O plus. That's how we got the H3O plus to begin with. All right. So the OH is added to the more substituted carbon of the alkene. The more substituted the carbon is, the faster the reaction. And remember, we did talk about this, that, more substituted carbon is more stable. So here you go, and then we can see that the relative rate is faster too. And that's because we can form a more stable carbocation intermediate. Here we'd form a primary versus secondary versus a tertiary. So this all kind of follows the same order. And we get our proton transfer. We have a tertiary carbocation right here, and water can act as a nucleophile and attack the carbocation intermediate. And then once this forms right here, there can be another water that can deprotonate this right here. And that's how you get this alcohol right here. So water functions as a base and deprotonates the oxonium ion, yielding the products. So the reactions and products of hydration are in equilibrium. We can exploit Le Chatelier's principle to control the equilibrium. So let's say, for instance, we want to make this product over here. If you put in more of this stuff and more water, you're going to go to the right. Now, if you if you increase the concentration of sulfuric, so in this case, you'd have to have dilute sulfuric acid. Sorry about that. So in this case, going to the left, if you increase the concentration of sulfuric acid, you take out water, you're going to be going this way. So it really depends. Do you want to synthesize the alcohol? Do you want to synthesize the alkene? So, here would be your two different reaction circumstances to do that. Or to push the reaction in the direction that you want it to go. Because remember, there's an equilibrium here. Let's get rid of this. There's an equilibrium here. It's now we decide, okay, I want to go to the left. So this is going to become real small if I choose these reaction conditions right here. So the stereochemistry of hydration is analogous to hydration for the same reasons. So if a new chiral center is formed, a mixture of R and S is obtained. As always, if a chiral center is formed in a reaction, then a racemic mixture is obtained. And that's because you're going to be protonating this, and then that OH can attack from the bottom or the top, and depending on the direction it attacks on, you're going to get the RS isomer. And here we have, 1, 2, 3. This would be R, and this must be the S then. Actually, I got that mixed up. This would be 1, 2, 3. This is the S, this is the R. Yeah. Any questions on that? When you look at the participants. Again, I just want to reiterate, this so that way, you can't say I didn't say this, but the exam is due tonight. So, if you are one of those students, and we do have a lot of you that have not completed the exam, I'm just letting you know, the exam is due tonight. So it is in your best interest to start it, immediately after class, or take a lunch break and then start it. But at some point in time today, that exam needs to be completed. And I'll send out an email reminder too, right after this class. So that's because the only reason why I remind you, because I want you to do well. I don't want you to forget about it. So Markovnikov hydration, H2O, H2SO4 has limited application. And that's because rearrangements often occur. And maybe if you're the chemical company, you don't want these rearrangements. You want to go in one direction. So oxymercuration, demercuration is an alternative. Markovnikov addition of hydrogen. So there's no rearrangements with this. But look what chemical you have to use. I've used a lot of mercury before, and this stuff, you just have to watch yourself working with mercury. So we are in the 4th week, so we don't have too much longer to go. So the mercuric cation is the Lewis acid in this reaction. What is a Lewis acid? We have to think about that, and that's going to be your electron acceptor. So when the pi bond, so they're showing you, the rearrangements, and this is not going to rearrange. So when the pi bond attacks the mercuric cation, a stabilized cation is formed. Okay, so here it's acting as a Lewis acid, right? It's acting as a electron acceptor. So it accepts those electrons. These electrons push right here, and we have this mercurium ion. It can go in equilibrium back and forth, but they're not going to have any rearrangements. We had that we still have that hydrogen right there, but it's not going to go ahead and say, oh, I want to move over here to the more stable, carbocation. That rearrangement is not going to take place with this situation. The only way you could find this out is to experimentally do this in the lab. So then you can see where it's helpful to go in the lab, because we can draw these mechanisms all day long, but if we don't experimentally test them, it may not give us the results that we want. We can guess and take good educated guesses about what might happen, but ultimately you have to go in the lab to test it. So the mercurium ion is electrophile, and it can easily be attacked by a nucleophile. So here we're showing it being attacked by a nucleophile. It says sodium borohydrate is generally used to replace the HGOAC group with a proton group via free radical mechanism. So the two reaction sequences provide the same products as acid catalyzed hydration. Here we had no rearrangement. Here we have rearrangement. So we have a mixture of products. Remember, in this case, we might get 60-40. In this case, on the bottom case, when we're using the mercury compound with sodium borohydrate, we're going to get no rearrangement. We're going to, preferentially get this in 94%. What that sodium borohydrate does, I'll come back here. There's some hydride, and it's going to push that mercury off. That's what's happening, and that's what they meant by this. And they're showing it to you right here. All right, so it's 10:55. It's time for a break. Let's come back in 10 minutes. Enjoy your break, and I'll see you soon. So we are re-recording now. We just got back from a break. We're going back to slide 40. We're going on to slide 42 is what I should say. Moving on to slide 42. We left off on slide 41 here. We're on slide 42. It says the hydroboration oxidation adds the oxygen, hydrogen, and hydroxide with anti-Markovnikov regioselectivity. So remember the anti-Markovnikov product would be the less substituted vinylic position. So hydroboration oxidation is also stereoselective. We're going to add them in a syn fashion. You can see syn means the same side. So it can be the up or it can be down. And these are enantiomers. Anti-addition is not observed. Here's the geometry and hybridization of a BH3 is analogous to a carbocation. You can see that the borane versus the carbocation. It has an MTP orbital. And what this does is they form dimers with each other. You can see this boron-boron dimer right down here. So the resonance hybrid reveals 3-center 2-electron bonds. It says the boron atom does not have an octet. You can count 2, 2, and 2. That'd be 6. So BH3 forms a dimer to help fulfill the boron atom's octets. So B2H6 can be stabilized by using an ether solvent so that an appreciable amount of BH3 is present. So they're showing you THF, which is an ether. Remember, an ether is an ROR. ROR, yeah. And we can see that here's our O, here's our R, and here's another R. The active reagent is BH3 THF, and the only way you determine this stuff is through experimentally in the lab. So hydroboration follows anti-Markovnikov. So we are going to go to the left substituted carbon atom, attacks the boron. And the more substituted carbon develops a delta positive, a partial positive, which triggers a hydride shift. We can see that hydride shift right here. Recall that the more substituted carbon will be better at stabilizing a partial positive charge. So that kind of makes sense why we're going in this direction. I do a good job right here of showing this right here. So if one BH3 reacts with 3 equivalents of the alkene, and the first step is repeated for each BH bond. So we just keep on repeating this process again and again. And you could just think about this as R, and you can repeat this 3 times or 2 more times after the first time. So that's why they said 3 equivalents of the alkane to 1 equivalent of BH3. So hydroboration follows anti-Markovnikov regioselectivity. Sterics also influence the regioselectivity. You can see that this is more crowded. This is less crowded on the anti-Markovnikov. That's another reason. Here we show hydroboration. We repeat this 2 more times and we get this. We can have oxidation. Here's a peroxide. So we can have proton transfer. And once we have the proton transfer, this can attack right here. That R group can move. You can see that R group move into the oxygen here. And then you just repeat. So there's a lot of repeating going on. So you're going to repeat that again. And then we'll have OR here and then OR here. So once we do that, we can take this hydroxide. We can attack at this boron center. Then we have an OR that's released. And that ROR can then protonate itself to make the alcohol. So we basically turned this alkene into this product down here, this alcohol. There's a lot going on there, so I'll just leave this here and you can think about it. If you have any questions, please ask me. So hydroboration is stereospecific. Only syn addition occurs, so that means that's the same side. So if only one chiral center is formed, a pair of enantiomers is formed by addition to either face of the alkene. So it can either go from the top or from the bottom, and they do a good job showing that right here. So hydroboration is stereospecific, only syn addition. If 2 chiral centers are formed, a pair of enantiomers is obtained. They show that pair of enantiomers, and they're adding on the same side. Here they're adding on the bottom, here they're adding on the top. So, when you go to predict the product for this, you're going to either have them both up or you're going to have them both down. And they show it to you, right here. For this addition, have this right here. This, it's either the OH is going to either be here and it's either going to be up or down. And in this case, it is up on the right-hand side. So hydrogenation is the addition of H2 across a carbon-carbon double bond. That means we're going to get rid of this double bond, this double bond right here, and we're going to fill it with hydrogens. And you usually do this with a platinum catalyst. So here's your platinum catalyst. An alkene is reduced to the corresponding alkane. So we're reducing it. And this goes to 100%. Hydrogenation is the addition of H2 across a carbon-carbon double bond. It's stereospecific, only syn addition is observed. So that means the hydrogens are going to add on both sides. So either here, up or down. So two chiral centers are formed. Only the stereoisomers resulting from syn addition are obtained, and they show that to you right there. So if these hydrogens are up, that means these groups are going to be down like this. So without the metal catalyst, the addition of H2 is too slow due to a very high activation energy. You can see this, without the catalyst, we're really not going to push that reaction. It's just going to be too slow. And they show a good job here of how this catalyst works. Here's your platinum. All these round spheres are platinum. So the metal surface binds the H2 and the alkene, which explains why both hydrogen atoms are added to the same side. The syn addition of H2 to a symmetrical alkene will not produce a pair of enantiomers. So a meso compound will be produced instead. So a syn addition produces only one product, and that's the meso compound. So hydrogenous catalyst does not dissolve in the reaction medium like platinum or palladium. A homogeneous catalyst does dissolve in the reaction medium, accomplished by using ligands with the metal. So we had the heterogeneous catalyst, and we had the homogeneous catalyst. It says, recall that the creation of one or two chiral centers results in a mixture of enantiomers unless a meso compound is produced. So creating one chiral center, we'll use these sets of conditions. We'll use the same set of conditions, but you can see how the substitution is different on the bottom one. So we'll call this one R1, R2, and with R2, we're going to have two chiral centers. And those chiral centers would be right here and right here, and this would be right there. So if a chiral catalyst is used, it is possible to synthesize only one enantiomer as a major product. So this can be accomplished by replacing the phosphine ligands on the Wilkinson catalyst with the chiral phosphine ligands. So we have 3 triphenyl phosphine ligands here. We have the chiral phosphine ligand and rather than the symmetrical phosphine ligand. So here, here they're saying this is a symmetrical, and we can change that up, with the methyl group and some other R groups. So if a chiral catalyst is used, it is possible to synthesize only one enantiomer as the major product. William Knowles developed a synthesis of L-DOPA using an asymmetric hydrogenation as the key step. So you can see, here we have the asymmetric hydrogenation of this pi bond right here. He later got the Nobel Prize in Chemistry in 2001. We're using a chiral catalyst, and we only got the one enantiomer. And it was the S in this case. So they were trying to selectively choose the S. And the reason why they do this is because sometimes chemical compounds are only active in the S form or the R form. So they want to preferentially select the S form in this case. If a chiral catalyst is used, it is possible to synthesize only one enantiomer. There was another person that showed that the chiral ligand by NAP also affords one enantiomer with high selectivity. So he showed, here's your chiral center right there. And for this work, he shared the Nobel Prize in 2001 with Knowles. So they did similar work. Halogenation, addition of 2 halogen atoms across a carbon-carbon double bond. And we can see this right here. This is a key step in the production of polyvinyl chloride, PVC. You can think of PVC pipes. So we have ethylene, we add chlorine to it, we produce this vinyl chloride, and we get this polymer, PVC. So halogenation is only practical with Cl and chloride and bromine. Halogenation with I2 or iodine is poor, and halogenation with fluoride is just too violent. That means fluoride is just too reactive. So stereoselectivity, halogenation occurs via anti-addition. So we can see this, and that's because when this bromine is going to come here, now that bromine is going to attack either here or here, which means it's going to be on the downside, and this is going to push. So let's just say, for instance, we'll go this one right here. Well, that's going to take it right there. So it's going to be on the downside. That's going to push this to the upside right here. So this will be here now. So bromine is nonpolar but polarizable. So that means when it comes in contact with a nucleophile that has some type of negative charge, there's going to be a dipole shift. a momentary dipole shift where there'll be a partial positive here and partial negative here. So it says the alkene acts as a nucleophile and the bromine acts as electrophile then. And here it says only anti-addition observed, so the mechanism is not consistent with the true carbocation intermediate. And that's because this stuff is getting in the way right here. You see that? That's going to be in the way, so it's going to want to go down towards the anti-addition. I say the formation of a bromonium ion intermediate is consistent with anti-addition. This intermediate is similar to the mercurium ion. Remember the mercurium ion, we had that we preferentially put, you know, our substituents on one side of the compound. The formation of bromonium ion intermediate is consistent with an anti-addition. We talked about that. Bromine attacks the bromonium ion in an SN2 process, giving the anti-addition. So that means it's concerted. So this is a concerted reaction right here. It's not stepwise. Halogenation is stereospecific. The stereochemistry of the Astardian alkene determines the stereochemistry of the products. So if we start with cis, we're going to get these two products. If we start with the trans 2-butene, we're going to get just the meso product right here. And just a small little bit of this is what this means. And then we come to this topic called, you know, we're going to react these bromonium ions with water. So halohydrins formed when the halogenation is conducted in water. So water can act as a nucleophile that attacks the bromonium ion. You know, obviously we're going to get the enantiomer. And there are many more water molecules compared to bromine ions. So the attack of the bromonium ion by water is more likely than bromine. So what they're saying is, yes, we do have this, but if we have this in water, this can be more abundant. So if we have, you know, 100 waters compared to maybe 1 bromine, you know, the water is going to attack before the bromine gets there. And you could just think of, well, if we have 10,000 waters versus 1 bromine. It says after water attacks, it is deprotonated to yield the neutral bromohydrin product. And here the product is called a chlorohydrin for this one. And here it's called a bromohydrin. And you can see that water serves as a base and can deprotonate that proton. The interesting thing is that the halohydrin formation is regioselective. So that means we're going to put the halide. So the halide adds to the less substituted carbon. So in this case, you know, the less substituted carbon would be on this side. And we can see that the halogen reacts right there. Now, if this were chlorine, it'd be the same thing, but this would be chlorine right here. So regioselectivity results from the water attacking the more substituted carbon. The faster then it attacks the less substituted one. You can see that we had the oxonium ion and it's being deprotonated by water. Regional selectivity results from water attacking the more substituted carbon. So the more substituted carbon has more cationic character. I mean, there's a larger partial positive here than over here. What they should have done was drop maybe that size versus this size. And this will be the last slide we do today. Dehydroxylation, addition of a hydroxide and hydroxide across the pi bond. We can see that right here. We're going to have OH and we're going to have OH and we produce ethylene glycol. So you can see how these starting products, ethylene, are helping us make these other products. The anti-dehydroxylation of the alkene is a two-step process. I guess we'll go on to the next slide just to show you the two-step process. First, we form the epoxide and we form the transdiol. So here they're showing you the formation of the epoxide. This is the epoxide right here. So we get that epoxide. And then a peroxy acid is used as a reagent. And then to convert the alkane to an epoxide, here we have a proton transfer, a nucleophilic attack, and then another proton transfer on the oxonium ion right here. So this is your oxonium ion. We have another proton transfer and we add the two OH groups, so we add the two alcohol groups. So that's it today. I hope you enjoyed the lecture. I will see everyone tomorrow. Just keep in mind the due dates. The test is due tonight, and good luck, and I'll see everyone tomorrow. Have a great day.